This video will discuss the solution to question 34. Figure 6 shows a particular dynamic memory implementation with CS is 10 femtofarads, CB is 100 femtofarads and VDD is 1 volt. What is the approximate function in time that node X follows just after the activation of the sense amplifier and while all transistors Q1 to Q4 are well in saturation so that the small signal approximation at the latch metastable point are still valid? So this is the dynamic memory chip that we're talking about, and in this question we're looking at the time-dependent behavior of the voltage at node X. This chip works in such a way that this capacitor stores a certain voltage, which is then, and to read out this value, this switch here is turned on, which means that this capacitor is connected in parallel effectively to this parasitic bit-line capacitance, CB, and as a result the voltage at node X will be a little bit higher or a little bit lower than some pre-charge voltage. This latch has its metastable point at the pre-charge voltage. So if the voltage at node X is a little bit larger than the pre-charge voltage, then the latch will ensure that the voltage at node X will be increased to the positive logical voltage value. When the voltage at node X is a little bit smaller than the pre-charge voltage, then the latch will ensure that the voltage will decrease to the lower logical voltage. And it does so with an exponential function in time. And that is actually why this latch is so preferred, because an exponential time response is a very quick response with respect to a linear or a quadratic response. So the correct answer here is E. The time-dependent behavior of the voltage at node X can be described by an exponential function in time of the form e to the power G.M over CB plus CS t, with G.M being the transconductance of the inverter at VDD over 2.